Okay, so this is my last lecture. The first 3 lectures were about physics in the lab, and I talked about actually I talked about 5 different real experiments, some of which have already been done, some not. Today I'm going to be talking about experiments that have definitely not been done, and about a theory which is only in its preliminary stages, but which I think is going to be very interesting in the future. So, what I'm going to talk about today in this last lecture is the relationship between possible experiments which will be optomechanical, which would of course be done on Earth, and the problem of quantum gravity. So the way one gives a talk like this depends very much on the audience. And my assumption here is that people are not specialists in gravity, so I will not be addressing the kind of concerns that people who are working in gravity would have. I'll mention them, but I'm not going to talk about them very much. However, at the end of this talk, I've put a long appendix for people who are interested in the technical side of it, which I will not talk about during the lecture, but anyone who wants to look at it is free to do so. Oh, and I didn't fill that in, so the first part of the talk actually is something which has got nothing to do with gravity, apparently, but which will be very important in any experiments which one carries out to check any theory of quantum gravity. So let me talk about those. So the first has to do with any interference experiment. Nowadays, the people in Vienna, they've acquired a certain name for doing experiments, interference experiments with larger and larger objects. I actually had a gallery of pictures of those objects, but I don't think we need them. The point is that they do 2-slit experiments with large molecules. Actually, what they do is, what they do is what's called a Talbot-Lowe experiment. This is where instead of one pair of slits, you have lots and lots of slits, and this allows you to focus things in one direction more easily. And the result, of course, is that they see an interference pattern with some sort of theoretical fit, and then they attempt to understand why the 2-slit interference is not perfect by invoking decoherence. And they argue that the decoherence is coming from collisions of the molecules passing through here with photons and gas molecules, which is these are very obvious decoherence mechanisms. So what I want to point out is that there's another mechanism which is in principle universal in experiments, but which most of the time isn't important, but it will eventually become very important in any experiment like this, which I call third-party decoherence. So imagine that we have a system, and in this case it'll be a large molecule, which can pass along one or other of 2 paths. Imagine that the coordinate of that system does not interact with an environment. Now, of course, the center of mass coordinate of a molecule does interact with photons and gas molecules, but it does not interact with the internal modes of the molecule. Why? Well, this molecule is moving in free space, so clearly there's no interaction. However, when the molecule interacts with the slit system, there's an indirect interaction via the slit system to the internal modes of the molecule. This is fairly obvious, but of course it's not being included in this discussion. So what we can say is that there's no direct coupling between the coordinate of the center of mass coordinate of the molecule and the internal modes, but there will be an indirect coupling mediated by the measurement process itself. So that's what this is supposed to show. Actually, the internal modes of the molecule are both rotational, it can spin, and vibrational. And there are a lot of them. So some calculations have been done for this, and I think it'll be interesting to compare with experiments like this. But the reason I'm telling you about this is because, of course, this sort of thing happens all the time. Anytime you do an experiment in which the experimental system itself interacts both with the coordinate that you're interested in and other coordinates, then you can have, in principle, this kind of third-party decoherence. Now, this is a problem of what I call a hidden decoherence mechanism, because it's not there when the system is just behaving normally. It's only there when you do a measurement. Another important point I'd like to make, which has been a little controversial, is that when people talk about how macroscopic an interference or coherence experiment is, there's a lot of talk, but not much calculation a lot of the time. So claims have been made, for example, that in the coherence experiments in superconductors, the number of particles involved in the Schrödinger cat state is of order 10 to the 9 or 10 to the 10, and the numbers are all over the place. So it's actually important to give a proper measure of this, and this was done in this paper and actually in these papers. And there's a brief discussion of it in the context of the two-slit experiment in this paper. And the numbers are interesting. So these are the way in which you determine these numbers is there are various quantum information theoretic measures that are applied. And I'm not going to go into the details. Roughly, the physical point is this. If you change, if a system can go along one of two paths, it will couple two environmental modes. But the coupling may be very weak, so the change in the modes can be very, very small. And so you may be changing a lot of modes, but you're changing them by a very small amount. And so a proper measure of how macroscopic this interference is gives actually rather small numbers. So these are the three experiments that were done, coherence experiments on superconductors, and these are the numbers that they find. They're not very big. In fact, the numbers that you find in the experiments that I showed you here are much bigger because you're actually separating the center of mass coordinate by a large distance. So actually, these really are the most macroscopic experiments that have been done. And so I'd like to summarize some of the problems that arise in any experiment where you're looking for large-scale coherence effects. One is one that I've discussed quite extensively, is that many of the decoherence sources are simply not visible in most of the experiments you do. I think I told you that when the first experiments were done on superconducting systems to look for macroscopic coherence, cat states, the estimates that were made using Caldera-Leggett theory of the decoherence rates were off by a factor of 10 to the 6th. And the reason was that they'd completely neglected the spin bath, that is, defects, nuclear spins, and so on. And this happens over and over again. You'll see experiments which claim to be testing quantum mechanics at the large scale, but actually, if they really are, then quantum mechanics has failed because the decoherence rates are much larger than the theory predicts. So that's why I actually showed you this experiment the other day where calculations were done of decoherence rates which actually agreed with experiment. That is not common. And the reason is hidden decoherence mechanisms. And a corollary here is that to simply parameterize decoherence by some noise in the system and use the fluctuation dissipation theorem is just basically wrong. It only works in situations where all modes are weakly coupled to the system and where the environment is completely in equilibrium with the system, which is certainly not the case for a spin bath. No one expects nuclear spins to quickly reach equilibrium, and they don't. That's why we have very long T2s and why we can do magnetic resonance imaging in hospitals. Now, as I said, some of these decoherence mechanisms are not even understandable in terms of a direct coupling to a bath. I just gave you an example. And the degree to which the system is displaying macroscopic behavior is often not clear. And all of these issues are related to the topic of quantum gravity and indeed any attempt to do macroscopic quantum experiments. So that's what I'm coming to now. So as I said, I'm not going to go into the deep problems here in any detail, because the real aim of this talk is to discuss what kind of experiments might be done. But I do feel that because this is not an audience of people in gravity, that it's important to emphasize how successful gravity theory is. I would say that in most ways, it's just as successful as quantum mechanics. And I want to just remind you of some of those successes and how extraordinary they are. We're all aware of the weak field experimental tests of general relativity. Now, this is actually a video, but I'm not sure how I'm going to get it to work. It's unfortunate because actually I can make these two pulsars spin around each other and emit gravitational waves. But actually, the way this program is set up, I can't make it happen. Unfortunate. No, sorry. But this is the first binary pulsar discovered. There are a number of binary pulsars known now, and there's even a triple pulsar. But this is the first one. And by timing the rate at which these go around each other and watching the decay of the orbit, we can fit to general relativity, and the fits are extraordinarily accurate now. The accuracy at which one measures these general relativist effects increases as the cube of the period of time over which you observe them, assuming nothing else changes. But actually, equipment gets better, so it's more than the cube. Another extraordinarily good test of general relativity in the weak field regime is gravitational lensing, and these are typical pictures. This is the image of a very distant galaxy, which is behind this one, and which would actually be invisible otherwise, because it's so far away. The agreement with theory is so good that this is now used as a tool for investigating things far away, as I'm sure you know. But actually, these tests are not the reason why people think that general relativity is such a great theory. The real reason is not precise observational tests. It's the fact that you can't do astrophysics now without general relativity. It's simply impossible to understand anything that people look at without it. And let me just tell you a few of those things. Supergiant stars, supernovae, the production of black holes. Stellar black holes are now very well known to exist. The supermassive black holes at the centers of practically all galaxies, we now know, and the incredible jets that come out of the centers of these galaxies. This is the galaxy M87, which is the largest galaxy in our region of space. Its mass is really very large. That is a mass of nearly 50 times the mass of the Milky Way. And the Milky Way is already a big galaxy. We're very lucky we don't live in a galaxy like this, because the central jet here has actually heated the entire galaxy to a temperature of 2 million degrees just by sweeping around, which means that there's definitely nothing living in this galaxy of any kind. I remember when I was a child, everybody said that this object here was two galaxies colliding. No, it's actually not. What it is two enormous masses of matter which have been ejected from a central supermassive black hole. And of course, we know that very recently there was an observation of the coalescence of two black holes, and the theory worked so well that it was possible, using pre-calculated forms for the decay, to fit to what was observed and immediately calculate all the parameters of this pair of black holes. So it's very important that all of the calculations of these forms were done before the observation, and it was simply a matter of fitting. And of course, in cosmology, we're also using general relativity. In fact, the very first prediction of general relativity to be verified was the Big Bang. Nowadays, people talk about the Big Bang in terms of the tunneling of the entire universe from one vacuum to another. That's where the inflationary universe scenario comes from. Whether or not it's correct is another question. But here is the final picture that we arrive at right now. This is a table showing the contributions to the energy of the universe coming from different objects and the contributions to the entropy. So you see that most of the energy is in stars and heated stellar dust. But almost all of the entropy, it's quite amazing, is in supermassive black holes. So this is the entropy that we think roughly is in the supermassive black holes. Actually, the energy of a single supermassive black hole, the entropy of a single supermassive black hole is more than all of the stars in the universe combined. It's quite unbelievable. And that's not even a big one. And we have actually a rather small one in our own galaxy. Luckily, it's small. Otherwise, we would not be here. And the reason why there's so much entropy is that the amount of information that you can store in the horizon of a black hole is quite unbelievably large. It's basically one bit of information for an area which is h bar squared in size. And in fact, a problem that is not yet understood is when a star collapses, how is it that the entropy increases by such an enormous factor during that process? And this is related to the information paradox in black hole theory. So there are many mysteries still here, but the observations make it utterly clear that the universe is pretty much completely controlled by these objects in its evolution and its both the past evolution and the future evolution. And all of these are things that we would not be able to understand or talk about without general relativity. However, there is a problem. And the problem is that we also think that quantum mechanics is correct. And these two theories don't sit easily with each other. So let me just quickly remark on what some of the things that we do know are, and also the problems that come from those. The first is we know that space-time has to be quantized. Every time anybody tries to cook up a theory in which space-time is classical and the matter is quantized, you get nonsense. If you just look at Einstein's field equations, you see that the right-hand side is matter and the left-hand side is space-time. And it just doesn't work. You get all sorts of paradoxes. Causality is broken, energy is not conserved, and so on. But if you try and quantize space-time, you end up with a problem, which is actually very simple to understand, although technically it's very messy. It's this. As you look at fluctuations of space-time that are shorter and shorter wavelength, and therefore higher and higher energy, because these fluctuations are just like photons, their energy increases with their wave number, then these fluctuate, if I take two fluctuations with wave numbers k and energies E, then they attract each other, because they have energy, and in general relativity, anything with energy, including space-time, attracts itself. It has a self-interaction. And that means that there's a problem, which is that the higher these fluctuations are in energy, the more and more they attract each other. And of course, in classical relativity, that's what produces a black hole. The space-time just gets more and more curved, and the curvature eats itself up because it attracts itself, and it just blows up, and you get a singularity. In the quantum version, we say that the theory is non-renormalizable. And in fact, nobody's been able to figure out a way to get past this, despite 50 years of effort. The third thing, but the key point is that this is unavoidable. There's no way around it. The third thing is that low energy gravity, quantum gravity, is completely well defined. In fact, it's the theory of low energy quantum gravity that's produced, for example, all these ideas of Hawking radiation, the Unruh effect, and so forth. All of that is low energy gravity, which is a perfectly good theory. It just ignores the high energy effects. It's rather the situation we had in quantum electrodynamics way back in the 50s. It apparently blew up at high energies, but it was obviously worked fine at low energies. But superpositions are not well defined in gravity, and I'm going to talk about that in a minute. Most important, gravity is very nonlinear. That's what causes this problem. And that means that any quantum gravity theory has to be very nonlinear too. And here is the biggest problem of all. Quantum mechanics is a linear theory, and general relativity is not. And so this is, for me at any rate, the biggest problem of all. You know, I have a lot of formal remarks here, which are of interest to people who are doing theory of quantum gravity. I'm only going to just say why I put them here for those who are interested. It's that if you want to set up quantum gravity, there's really no reasonable way to do it apart from path integral theory. But it turns out that technically it's very complicated, and that's what these two slides are about. And the biggest problem of all is that if you do try and sum over all configurations of space-time, then you have to sum over different topologies, and so you get these amusing pictures that people make. Here's different topologies, and it turns out that this leads to big problems, trying to sum over these topologies. And the second thing is that the space-time, if you sum over two different space-times in a path integral, in other words, if you try and superpose two different space-times, then the causal structure of those two space-times is different. So one space-time may have event A before event B in time, the other one would have it after. And this means that fundamentally you can't actually define any quantum theory on that because you've completely lost the normal causal structure of the theory. And this is a problem which is still with us. So you say, well, why would anyone want to work in this field? It's obviously completely impossible. What's the point? Well, the point is partly that, as I told you, general relativity works, and so we can't really say that we have a theory of physics until we've managed to fix this problem, find some new theory. And of course, that's what string theorists try and do, and also loop gravity people. But the other reason is the one I want to talk about today, and that reason is that it should be possible to test some of this in the lab, hopefully in the next 10 years. Various experimentalists in this field like to lay bets about when the first experiment will actually do such a test. It's quite amusing to listen to the guesses for when that will be. But most of them think it'll happen before the year 2020. So, low energy gravity, what is it? Well, basically it just says that when we calculate something, we do sum over different configurations of space-time, but we make sure that they're all ones in which space-time bends very slowly in time and space. In other words, they're all low energy. So when I write down, for example, the propagator for a particle as a path integral, the propagator for the particle, if you just assume that space-time is flat and you stop worrying about it, is just, we already saw this, but for a particle go between x prime and x, and we just integrate over all paths with this weighting factor. But now, if we allow gravity to be involved, then the action of the particle depends on the space-time metric. And I have to integrate over all possible space-time metrics. Now, as I told you, that integral is pathological in general, but if we confine ourselves to integrals over low-energy configurations of space-time, it's perfectly well behaved. And as I said, this is the way that, for example, people have worked out things like Hawking radiation. Actually, for Hawking radiation, you don't even vary the background space-time, you just keep it in some curved configuration. And, of course, you know, there are lots of predictions that come out of this, and one can set up a theory in which you sum over diagrams and so on. And this is well understood. So here's the problem. This is the problem that's really relevant to experiments in the lab. So let me spend some time on it. Imagine that I have a mass, and this mass is going to go along one of two paths in a quantum interference experiment. And I'm showing one of these paths as apples and the other is oranges. In English, you talk about things being apples and comparing apples and oranges, meaning that they're not the same. I think in French it would be comparer les torchons et les serviettes, something like that. But anyway, the whole point is that in ordinary quantum mechanics, we would simply treat these two paths as paths for the same object, and there would be no problem. We would sum, take the interference, and voila. If we want to do a measurement here, if taking into account that these objects have mass, then we would, for example, use a torsion balance, which would be sensitive to which path the mass moved along. And this torsion balance, of course, is detecting the gravitational field from the mass And so, for example, in the way I've shown it here, if the mass goes along the orange path, then the torsion balance is deviated. If it goes along the apple path, then it's not deviated. So after the experiment is done, we expect the torsion balance to be in a superposition of states before we have a collapse of the wave function. And of course we will, because this is how we do quantum mechanics, eventually have to talk about a collapse of the wave function because we want a definite result. Good. And of course what we're really measuring here is the distortion of space-time caused by this mass as it moves. And that distortion will be different here depending on which path you go along. Very nice. So how do we describe this in ordinary quantum mechanical language? Well, we have to take account of the fact that the wave function here includes not only the wave function of the mass, which I'm going to call phi 1 or phi 2, and these coefficients here, oh, that should be an A2, sorry. But it also includes the space-time configuration, which is associated with that mass. So in other words, my state vector has to include both the wave function of the mass and of space-time. Now, of course, in ordinary experiments in the lab, we completely ignore this, and we just forget about space-time. We assume it's flat, and then we just have this classic interference. We say that we project the Hilbert space state onto a position state vector, and then we get a wave function of this form. And then when we calculate interference, we just calculate this overlap. Fine. But remember, this overlap assumes that we can integrate over R, the real space, and that they have the same R, the same real space vector, the same, as well as the same time if it's non-relativistic. But that doesn't work in general relativity, because in general relativity, these two metrics are different. Therefore, they have different coordinate sets. And in fact, if you assume this is a quantum field theory, the vacuum of the two metrics is different. This is what's responsible for things like the Unruh effect, the fact that if you change the state of the object, then the vacuum changes as well. So we find that we have to compare now state vectors, phi 1 and phi 2, but the problem is that phi 1 has to be, the inner product has to be taken with R1 and T1, and phi 2 with R2 and T2. And in fact, the way that people in gravity say this is that time doesn't even flow in the same way in the two space-times. So there's a problem here. We can't compare these two metrics, and therefore we can't take this simple product. Formally, this is a formal problem. Now many people say, who cares? It's just formal. Somehow physics will take care of it. We may not know how to describe it properly, but physics will take care of it in a real experiment. But the problem is more than that. There's a physical problem too. Supposing I allow the wave function to collapse. There's two different metrics here. If you collapse it, it's got to suddenly go over to one of them. But you can't do that in general relativity. You can't suddenly change the metric. If you do, you create a singularity. And you certainly won't conserve energy. The other thing is that, as I said, the vacuum is different for the two. So there's actually a physical problem, and the physical effects associated with this do exist. Things like, or at least we believe they do, things like Hawking radiation and the Unruh effect, they arise anywhere where you have accelerations or curvatures. Now you might say, well, who cares? Again, these are small masses, these are the small effects. But actually, if you calculate the way in which time evolves in these two different superpositions, the effects are measurable. We know that the global positioning system depends on rather small changes in gravitational field, and yet they're easily measurable. So this is not something beyond the reach of the lab. So what do? We have two theories, each of which works incredibly well, each of which has predicted unbelievable things, which have been seen. And yet they don't agree with each other. So the idea is we do need a new theory, but it's not going to be easy. So what do? So this is where I'm going to describe briefly a theory which attempts to deal with this problem. And I'm going to do it in an informal way. I'm not going to go into the formal details. So where does this theory come from? Well, it comes from, roughly speaking, a thought experiment. So imagine that I want to decide how to measure both time and space in general relativity. Well, it's an interesting feature of general relativity that you can define the phase along a Worldline. This is the phase that one sees in any interference experiment, without defining a metric. All you have to do is measure proper time along a path, which I haven't shown. And the proper time that you measure along that path is actually related to the phase that will evolve, and that proper time actually depends only on the mass of the object. So the metric, on the other hand, can only be determined by comparing two paths. And in fact, the standard way of doing this is to send light signals back and forth between paths. And this allows you to, as it were, manufacture a metric. So these two are actually distinct from each other. But this is interesting because the equivalence principle tells us that gravity has no way of distinguishing between particles, between different objects, except by looking at their energy. So general relativity doesn't care whether it's a fermion or a boson, an electron or a proton. All it cares about is what is its local mass energy. But that tells you that general relativity can't tell the difference between two particles going along two paths or a superposition of two paths for one particle, because it's just energy momentum as far as gravity is concerned. In other words, these two situations are not distinguishable for gravity. This is where two particles come in and go out. And this is where they swap. It's totally impervious to the difference. And moreover, as I said, it can't tell the difference between a superposition of two paths for one particle and two paths for two particles, provided the masses are all the same. So this suggests a possible generalization of quantum mechanics. It's this. We replace the path integral for a particle here, which, as I've described many times, we sum over all possible paths, with a rather different formula in which we allow correlations between the different paths. And I'll show you this with a picture. Normally in quantum mechanics, we sum over all possible paths between x and x prime. That's it. So this is supposed to mean sum over all possible paths. That's what this Feynman diagram means. But now, supposing we allow correlations between pairs of paths and triplets of paths. Now this builds in the effect that I'm talking about because it allows gravity to sense not only the interaction between two paths which refer to two different particles, but also to a pair of paths for the same particle. In other words, this correlation that we're looking for is going to come from space-time itself. Another way of thinking about this is to say that space-time notices where mass is, but it doesn't distinguish between two paths for the same particle and two paths for different particles, because it's only sensing energy momentum. So this is rather radical because it means that the superposition principle is broken. Why? Well, the superposition principle in path integral theory is expressed by saying that you sum independently over each path. That's just superposing different time evolutions. If we put a correlation between paths in, so here what I'm doing is I'm summing over all pairs of paths, that's n equals 2, all triplets of paths, all quadruplets of paths, with gravity operating between them. But that means there's a correlation between the paths, which means the superposition principle is no longer valid. So this is radical. Nevertheless, it's precisely the kind of nonlinearity which gravity brings with it, which you can't avoid in gravity. So that's why we're doing this. So I'm not going to describe the mathematics, but the way you do this, the way you express these correlations is that as you functionally integrate over all possible configurations of the space-time in that sum. And that's how it's done. So the way I'm going to explain it now is I'm going to ask, in such a theory, how does a particle now propagate? In ordinary quantum mechanics, as you know, you sum over all different paths independently. What happens now? So this is a single particle moving from one point to another. So this would be ordinary quantum mechanics. This is the propagator between 2 points for a single particle. And remember, because we have now got to look at gravity, we've got to also include gravity in the path integral. But now we also have pairs of paths with their each having their action, and they are linked by gravity. And the easiest way to understand what's going on here is to see that this will cause exchange of gravitons in perturbation theory between paths, two different paths for the same particle. And these are the kind of diagrams that you get. So remember, this path and this path are for the same particle, likewise here and here. Okay, well, you can do the calculations, and as I'm going to show you, you can understand them intuitively in a very simple way. So let me not go through how the calculations are done, but just tell you what the answer is. An extra phase is now accumulated in the time evolution for a particle going between two places, and it depends on what, so this is the pairwise exchange between pairs, this is between pairs of paths only, and it depends therefore on the path followed by each of the two paths, Q and Q prime. So this is phase depends on each of those paths. Well, I'm now going to look at what happens when the particle is moving slowly, which is what we'll be looking at in a lab. We then find that it looks as though there's an interaction between the paths which has, first of all, a Newtonian component. This is the gravitational constant squared, this is the mass squared, and this is the distance between the paths. So this just looks like Newton's attraction, and that's what this first term is. Now there are corrections to this. This is a correction, this is the Schwarzschild radius of the particle, so it's very, very small, so this is a small correction. And this is the Planck length of the particle, so this is also very small. So we can ignore these in an ordinary lab experiment. And then we find that the phase just looks like this. This is the distance between path 1 and path 2. And this is the gravitational Newtonian coupling here. It goes like the mass squared with g. And this is a phase. This is e to the I times this. So basically what we're saying is that if two paths are close to each other, then they'll strongly couple. If they're far from each other, they won't at all. Now this should remind you of what I was talking about before. It looks a bit like ordinary environmental decoherence. But as we'll see, it's not. But the most important thing is that it tells you that if you take an ordinary particle, try and propagate it from one place to another, then with this mechanism, different paths for the particle find it much more difficult to separate from each other because they're attracted to each other. So I call this the path bunching effect. So if I just propagate an electron through a two-slit experiment, this mechanism, if the gravitational attraction is strong enough, stops the paths from separating, and it's going to kill interference. Now you say, well, the mass of an electron is really small, so obviously this doesn't matter for an electron. So how big does the particle have to be? Well, the way to think about this is just with your ordinary intuition for bound states of the hydrogen atom, except that instead of a Coulomb attraction, we now have a Newtonian attraction, which is much weaker. And so there are a number of scales here. The Newton radius is the gravitational analog of the Bohr radius. And this is a plot of that radius for particles of different mass. This is the mass of the electron, the mass of a hydrogen. This is 10 to the 7 hydrogens. And this is this analog of the Bohr radius. So you see that for an electron, it's very, very big. It's actually 4 million times the Hubble radius. But it falls very quickly. So that when we get to 10 to the 7 hydrogen masses, it's down to 1 meter. And actually, if we go to a mass of 2 times 10 to the minus 5 grams, that length scale is down to a Planck length. So this Bohr radius, the Newton radius, collapses very rapidly as you increase the mass. Then there's the analog of the binding energy in the Coulomb problem. So this would be the binding energy of a hydrogen atom, 13.6 electron volts. But here, it's in this Newtonian potential, and this binding energy increases incredibly fast. Actually, it goes as the 5th power of the mass. So for an electron, that binding energy is 10 to the minus 86 electron volts, completely negligible. But as we increase the mass, when we get to 10 to the 7 hydrogen masses, that energy is 10 to the minus 30. But if I go to 10 to the 13 hydrogen masses, it's now an electron volt, and so on. So what you see is that as we increase the mass of a particle, this mechanism goes from being completely unimportant to overwhelmingly important. And there's a very sudden crossover at a certain mass to a regime where the paths can no longer separate and where, in fact, quantum interference will no longer operate because the paths cannot separate for interference to happen. Now, of course, the problem with this calculation is I've done it for a single particle. In reality, a solid, an object with a mass of 10 to the 10 hydrogen atoms is not a single particle. It's spread out. So we have to do the calculation for that, which is more complicated. But we will see that no matter what is the distribution of mass, eventually the center of mass of the object can no longer form superpositions that are separated by large distances. If you like, the paths are bound in this potential and they can't get out. And I'm not going to say anything about the formal structure. That's for people who want to look at the details. And as I say, there's a long appendix to this lecture for those who want to look. Just one thing. People often ask me this. I've had many conversations, for example, with Frank Lalloy about this, which is how do you deal with measurements in such a theory? Because after all, in conventional quantum mechanics, we're supposed to have a collapse of the wave function, which is not, if you like, in the Schrödinger equation. The interesting thing about this theory is that what you find is that when the mass is sufficiently large, we have a mechanism which looks like a collapse. But it's not quite the same because it does not, there's no decoherence involved. And you can actually calculate this out. And what I'm going to show you here, that those of you who want to look at the details can read this. It's also in the papers. But this blue line here is showing you the superposition of two paths for the apparatus, which is considered to have a large mass. And the red paths are for the system. And this green thing here is actually the interaction between the apparatus and the system. And what's interesting when you do the calculations is that the moment you switch on the interaction between the apparatus and the system, the system, which is considered to be microscopic, is of course now coupled to the apparatus, and the apparatus can't form superpositions, and once the coupling occurs, then nor can the system. And so the measurement is described in this way. What we see is that the interference can no longer occur once the system is coupled to the apparatus. Now, of course, the dynamics depends on the coupling, and it doesn't happen immediately. What you see is that the interference collapses over a time period which depends on the details. But one can work this out. So now I want to talk about an experiment. That's ultimately what we're going to be talking about. So in this lecture, I began by talking about experiments, and now I'm going to finish, but the experiment here is a little different. It does not involve, for example, superconductors or ions, or molecules in a two-slit. What it involves is an optomechanical system. So there have been a number of discussions, and I'm not going to talk about all of the different experimental ideas here. I'm just going to give you one example so that you can see what sort of ideas are being talked about. And the example I'm going to give you is the first one that was discussed in the literature. So actually, the experiment that I'm talking about here was proposed in 2003, and of course it has not been done yet. So the basic idea here is that because we're looking at gravitational effects and their effect on superpositions, what we want to do is have a large mass, and we want to put it in a superposition of states where it's in two different positions. And if possible, either hold it there or make it oscillate so that the two branches of the wave function come together and then apart. And this is why there are so many experimental designs now. There are different ways of doing this. But the general idea is we want the two paths corresponding to two different positions of the mass, we want them to interact gravitationally. And of course, there have been a number of theoretical analyses of how this would work, both in a stochastic theory of quantum mechanics, a so-called collapse theory. Penrose has given an analysis. There's an older theory of Kibble, which could be used to analyze it. But I'm going to talk about how it works in the theory that I've showed you. Anyway, a number of experiments have, for example, involved a freely falling mass with a superposition of two different positions, which actually would separate in time. This is somewhat similar to the experiments with neutrons, the COW experiment. But I'm going to talk about a situation where we put a resonator into a superposition of different states. And this is the design that was first discussed. We have two cavities. This is a stationary cavity. And this one, however, one of the mirrors is on a spring, or it can be a spring or a cantilever. Now, what that means is that if there is a photon in this cavity, it will actually push the mirror back slightly. So what we then do is set up a situation in which we have a cat state, that is to say the photon is in a superposition of states of being either in cavity B or cavity A, which of course will then mean that the superposition will involve the mirror and its position. So we can write a state which initially would have simply involved a linear superposition of photon in cavity B or photon in cavity A, but now we have to involve the mirror state, and this produces something which in the design here, where the photon actually, oscillates back and forth, it has a situation in which you have a superposition going back and forth. You could make it stationary, but they wanted to make it oscillate. And this has been discussed in these papers. Another alternative is where you have a superposition in a crystal between 0 phonons and 1 phonon. Now, of course, in a real experiment, it's very hard to reduce environmental decoherence effects, which was the subject of my first 3 lectures. And it was also the subject of what I said at the beginning. However, a key point here, and this is really important, is that the way in which the gravitational effects change the experiment is completely different from decoherence. So, for example, you'll see that changing the amplitude of the oscillations completely changes the gravitational effects, but of course it will hardly affect decoherence because the decoherence mechanisms are internal. So they're not going to depend on what is the amplitude of the oscillations. And this is what's important. As I said, to do the theory that I was explaining, you have to redo what I was talking about now for n particles, which is complicated because we're now dealing with a mass here, this is the oscillator, which is made up from lots and lots of atoms with their electrons and so on. And so we have to adapt the theory that I talked about. The good news is that we actually have a very good theory of the dynamics of these individual atoms and how they move together. It's called phonon theory. So the typical spectrum of an insulating solid looks like this. This is the wave vector Q for the phonons, and this is their energy. And, well, this is for a simple solid. We have acoustic phonons and optical phonons. And if I now want to analyze the motion of all of the atoms in here, I can analyze it using this phonon spectrum. If I want to rewrite this as an analysis of all of the different paths of the ions, I simply Fourier transform that to get the characteristics of the different paths. And the fact is that in a real crystal, we can calculate all of the characteristics of these phonons very well. This has been done numerically for many years, and we can also measure them using neutrons. And we can measure the phonon frequencies. So this is something that's actually very well understood in a real system, so much so that we actually also know how to calculate the interaction between these phonons. So it's something that's been perfected over a very long period of time. That means that we can actually calculate the behavior of all of the paths of all of the different ions in the crystal in an experiment like this. And if we do that, well, the way we want to set up an experiment is we simply apply an AC force to the oscillator. We want to drive it, and then we want to look at the frequency, we want to look at oscillations, and we want to look at interesting coherence experiments. Now, I'm going to give you an intuitive description of what happens. If I simply look at the dynamics of the coordinate of this oscillator, these gravitational interactions have no effect at all. So if I look at, for example, correlators of the position of the oscillator at different times, it'll look exactly like the original oscillator without the gravitational effects, except, of course, that there'll be damping. But the damping is not coming from gravity, it's coming from ordinary decoherence. But here's the interesting thing. The coordinate that's conjugate to position for the oscillator is momentum. And if I look at the behavior of the momentum, I find that there's actually, because of the binding, the CWL mechanism, this gravitational mechanism, it stops paths from separating in real space, which causes there to be what looks like an effective potential and momentum space operating on the dynamics. So if I now ask, what does the dynamics of the oscillator look like in phase space, I find that the momentum-momentum correlations are changed, because it looks like we've added an extra potential to the harmonic well for the momentum. So we can calculate the numbers here for ordinary solids. We know how far apart these paths tend to be and so on. So I've just given the details here for those who are interested. And this is what we find. We find that the propagator for an oscillator looks like the ordinary oscillator in position space, but there's a renormalization here which operates only on the momentum coordinates of the oscillator. So that means that if you wanted to test a theory like this, you would actually look at the momentum correlations of the oscillator. Actually, you would also see it in correlators between X and P for the oscillator. And you might, so then the interesting question is, what mass will give us a crossover? Actually, this mass is larger than people had been saying. It turns out that for pretty much any solid, the crossover mass is 10 to the 18 hydrogen atoms in a theory like this. The reason it's not smaller is because, as I explained before, a real solid is spread out. So these gravitational effects are now spread out, and they're not nearly as severe as they would be if it was concentrated at one point. But as you see, we eventually get a crossover. What does this mean physically? It means that if you have a solid whose mass is greater than this, then you will not see interference of the kind that is observed, for example, in Vienna for a two-slit. Well, you say, we're very far from that. The experiments in Vienna, for example, have looked at superpositions of masses going through two different slits of order maybe 10 to the 4 hydrogen atoms, much smaller. People who work on large oscillators will come back and say, well, we have very, very large Q factors, so we expect to see coherence on a much larger scale. We'll see. Nevertheless, that is the prediction, that this mechanism, which as we see comes from gravity, will only operate for masses larger than this. But such an experiment has very attractive features. I mean, it's essentially an attempt to do a Schrödinger's cat experiment with an oscillator with a large mass, and to see whether there are any fundamental limitations coming from mechanisms that are not just ordinary decoherence, and of course which lead to a breakdown of quantum mechanics. And as I said before, key point is that the correlated Worldline correlations, that is these gravitational correlations, and the path bunching mechanism do not involve decoherence, and therefore this is not a decoherence mechanism. So this is not attempting to solve, if you like, the measurement problem with decoherence. It's a mechanism in which the measurement problem disappears because quantum mechanics itself stops working for sufficiently large masses. But you will only see it when those masses are involved. So if you ask, well, when... this is not a wave function collapse in the traditional way, in other words. But if you ask, when does this operate? It only operates for large masses. And so from that point of view, you can say that superpositions will continue to exist until you get to that mass scale, even though it may be very hard to see them because of decoherence. Okay, so that's an informal view with formalism for those who want to read it of this theory. And it brings me actually to the end of the course, most of which was spent on discussing pretty down-to-earth mechanisms operating in the lab and discussing systems which are related in some way or another to quantum information processing systems, systems like the icing model. You don't have to be interested in quantum information at all to look at these models. The quantum icing model is very interesting in its own right. But that, of course, is one of the reasons why people are looking at these models. So I guess my last slide is to thank a lot of different people here and elsewhere. So the people on the left are people here in the Collège de France who have been involved with my visit. These are people whom I've talked to a lot while I've been here as well. And then these are people who I've talked to a lot in this work outside Paris over the last couple of years. In fact, some of them I've collaborated with, for example, Gordon Semenoff. And then these are people whom I've worked with in Vancouver. And I'd like to thank all of them. And this is actually where I did most of this work on this island. So, thank you very much.